Hi, everybody. I'd love to introduce Connor Coley from MIT, who's been, well, connecting ML techniques to accelerate the scientific workflow for chemistry. Welcome, Connor.
Excellent. Thanks for having me here and giving me a chance to share a little bit about our work. Let me go ahead and get things set up. Hopefully you can still see everything all right, and we'll get started. So today I'm going to share a little bit about how we think about modeling chemistry. We're going to focus on the use of sort of AI and machine learning methods, targeting synthetic organic chemistry and analytical chemistry, and we'll talk a little bit about why those are important and, again, the specific approaches that we're taking. I'd like to start off just with a reminder that small molecules are this sort of really interesting and diverse modality. Small organic molecules, right, we typically think of them as being under maybe 500 grams per mole or 500 Daltons. They look like chemical structures, like they're drawn on the slide here, and each of these different structures exhibits a different sort of property profile and set of functions. So just by rearranging, right, the same familiar elements, right, carbon, nitrogen, oxygen, and just a handful of others predominantly, we end up with really interesting arrays of diverse functionality. And so that ranges from, sort of therapeutic applications where you might interact with target protein of interest, antibiotics, pesticides in agriculture, to also applications in material science, defense, materials for batteries as well. There's really a whole host of applications. And I think it's very interesting to think about small molecules as this design modality because the same opportunities to achieve this wide range of function means that it can be quite difficult to find the right structures, right, that have those functions. People like to estimate the size of chemical space and think about the vastness of this search space. And so we can think about addressing this complexity and addressing this vastness with different sorts of computational tools. So in particular, the way that we sort of view this problem of molecular design and discovery is as a multi-objective optimization problem. We'll typically go through different design cycles and iterative rounds of improvements where each time we have to answer somewhat challenging questions about what we're trying to make, how we're trying to make it, and analyzing then the results of that experimental attempt. And so given the difficulty of navigating these kinds of design cycles, there's a lot of interesting modeling questions that arise, right? Specific problems that might be useful to solve, right, with computational techniques to accelerate this overall process of discovery. That's the hope. So some of the questions that we try to answer include predicting different sort of reactivity properties, other properties also of small molecules, coming up with new structures, trying to balance information gain versus cost of these kinds of experiments. And really sort of throughout what we do, we think about the role of AI and machine learning and the needs to adapt these modeling approaches for the peculiarities of chemistry. And so in our group at MIT, we've got a number of different research threads within this broad landscape of AI for science or AI for chemistry. Again, some of those relate mostly to synthesis, which we'll spend some time talking about today, and how we understand what chemical transformations are possible and how to use them to access new structures. We think about AI for medicinal chemistry and trying to design new molecular structures that have the kinds of property profiles we're after. We can do this design with consideration of synthesis as well. These are not decoupled. And then we also have some work in AI for analytical chemistry, where we're thinking about the analysis of complex mixtures and the understanding of what molecular structures might be present. Again, throughout, we have to have these considerations of what is the modeling toolkit that we're using to address these challenges, and how do we think about the needs of chemistry as distinct from the needs of natural language processing, computer vision, other disciplines, and what does that mean in terms of model architectures? What kind of data do we need to accomplish these kinds of data-driven goals? And then what's the opportunity to connect sort of AI-informed planning with robotic experimentation? Now, we're not going to have the chance to talk about sort of all of these today, and we're going to really focus in on synthetic organic chemistry and analytical chemistry as some examples of what it is we do. But before I actually start talking about the contributions that we try to make in this space, I want to spend a moment thinking about the sort of history behind some of these problems. So, computation and AI for chemistry is quite an old and established concept. It's definitely not anything new from the past couple of decades. So back, starting in the late 1950s, 1960s, folks were building computer programs to help with the process of retrosynthetic analysis and coming up with recipes of how to make new molecular structures. The early days of this followed the early days of chess playing programs where maybe experts encoded rules, heuristics, and knowledge, and then computers would apply those rules algorithmically to explore the combinatorial space of options. And we'll define this task of retrosynthetic analysis more concretely soon. Folks have also been trying to build models to understand reactivity trends since the 1930s and very commonly since the 1960s as well. The idea is that we can try to connect aspects of molecular structure to the properties they exhibit or the reactivity that they go under or undergo, sorry. And so this is where we might think about building these models that understand structure function relationships. And again, even though we continue to do this in the present day, and we've developed a number of different modeling approaches, the fundamental ideas and objectives are decades old. Likewise, predicting analytical chemistry aspect or how molecules might look through our sort of different spectrometer based analyses, right? Like mass spectra in particular, that's something that's quite old too. So back in the 60s, right, with the sort of early approaches to automate scientific discovery, the Dendril program was one of the first examples of applying sort of AI concepts to science. And Dendril was a program to do mass spectral prediction and help elucidate chemical structures given their fragmentation patterns. And again, this started with rule-based systems and it has since evolved. Right. So with this backdrop, right, again, I think it's important to keep in mind that many of the long-standing challenges in these fields are long-standing challenges, right? They're not new tasks per se, but the way that we can approach them and our ability to gain traction has evolved, right, in recent years. So we don't have time to talk about all the different concepts that might be relevant, but we will start off with synthetic organic chemistry and thinking about how models can be built to understand chemical transformations and designing processes to access molecular structures. Right. So a synthetic route or a synthetic plan is a recipe, right? It defines the series of operations to access a product molecule of interest, in this case, palbociclib, drawn here. And it tells us what starting materials we can purchase, how we might react them together, and what intermediates we might then form and isolate, and then how to carry those forward through a series of steps all the way up to the final product or the final chemical structure we'd like to synthesize. Now, when humans learn how to do this, we learn it as a process of retrosynthetic analysis where we start with this target structure and we identify reverse transformations to simplify the structure further and further back until we reach starting materials we can purchase. Okay? And just like how humans do retrosynthetic analysis, that is how programs are typically taught to think of this as well. We provide this structure as input, and then the programs try to work backwards and output this full recipe, including all of the other bits of information that you see on the slide. Now, why do we care about coming up with recipes for new molecules? Well, obviously we have to physically produce molecules in the real world for them to have any benefit or function in society. But even during discovery, when we're just trying to get information out, we typically use synthesis as a constraint, or at least as a consideration, when we think about what molecules are accessible within this vast search space of all possible molecules. And so if you go online right now, you can look at chemical vendor catalogs, and they're willing to sell you tens of billions of molecules from these make-on-demand libraries. And these are libraries or catalogs of chemicals that don't exist yet physically, but they believe they can access through robust chemical reactions. And so generating these libraries benefits from an understanding of chemical reactions, and what's possible and what isn't possible. Now, this is just looking at chemical vendors in these libraries, but we can also think about the use of generative modeling. But of course, generative AI takes up a lot of space in conversations around AI and science these days. And generative models can invent new molecular structures that don't exist in these pre-enumerated libraries. But sometimes they generate structures that don't look so reasonable, and it might pose challenges in terms of synthesis or in terms of stability. And so really thinking about using synthesis as an evaluation tool for generative models is also something that we've really done in recent years.
So question.
Now, yeah, please.
It looks like you've chosen a particular abstraction level. You're not going in the story via molecular dynamics, where you say, I have this molecule and it might transform to these other molecules, from first principles. This is more like a search the space of possible game moves, where a separate model tells you what moves are possible.
That's right. Yep. So reactive molecular dynamics and like true first principles evaluation of reactions can't cope with the types of transformations and complexity that we're talking about here. And so we do think about this as one level of abstraction higher, where exactly it's thinking about, what are the game moves to do this process, but also you have to learn, right, or infer, what are those rules? And that's a great point, and we'll come back to that that concept exactly.
Okay.
Yeah. Now, it turns out actually that the game is different also, depending on who you talk to. Most people, right, when they think about this general task of synthetic planning, they'll think about just what's known as retrosynthetic analysis, right? So taking a molecule you want to make and finding this tree that shows the structure of intermediates and starting materials and tells you roughly what that tree should look like. But each of these arrows is a chemical transformation, and each of these arrows has an extraordinary amount of detail that could and ultimately does need to be specified. So at a basic level, that might be sort of what additives like catalysts and reagents, acids, bases, solvents might be relevant. As you go further in this sort of elaboration process, you'll also need to worry about precise quantitative details, like how much of each component to add, what temperature and time to use. And so depending on who you talk to, right, the goals are different. Sometimes it's sufficient to just do this sort of first level of abstraction, where it's a very coarse map of what this pathway might look like. But sometimes you really need to know these details to understand whether you have a good solution or not. And in particular, if we're thinking about the interface between the sort of planning and robotic execution, humans can infer missing details. These sort of automated platforms needs to be told at some level. They need to have a way of filling in all of the missing information. And so we think a little bit about the different levels of abstraction in these synthetic plans as defining, right, different modeling goals. But let's talk about the rules for a second. What defines what's possible at each chemical transformation step? So chemists like to communicate some of these rules in these sort of encyclopedic-esque textbooks of named reactions and transformation rules. They're typically communicated as subgraph patterns, or these transformations that say how one general subgraph might transform into another, and that forms what's known as a template that can be applied in new contexts. Now, these templates are typically drawn in a way that's more human interpretable than what's shown on this slide, but what's here on the slide is an example of one such template from Cynthia, which is an expert program for retrosynthetic analysis. And so in Cynthia, you have these expert chemist encoded transformation rules written down as these reaction smart strings, which is just a linearization of the subgraph in a depth first search. And this pattern basically defines the transformation. So if in a molecule you'd like to synthesize, you see this subgraph present, if the subgraph matches the molecule you'd like to make, this will generate a recommendation of reactant species that might be used to create that molecule. Again,
But
human experts.
are
Please.
these always trees, or can you have cycles in these chemicals?
You can have cycles, yeah. So you can also have cycles. So they're graphs, not trees.
So then, don't you have a problem with like linearizing graphs, and it's not a unique way of doing it? So, like, it has implications for searching over the space and so on.
Yeah, there's heuristics that work fine for canonicalizing the
Mhm.
traversal order of these that at this point are fairly robust in cheminformatics.
Okay, that helps. Thank you.
Yeah, yeah. So you just sort of have a token for a ring opening and ring closure down the road, and yeah, there's heuristics to define the precedence ordering of atoms. There is a non-uniqueness, which maybe is a sort of a subtlety that we don't have to get into too much, but if you in general have this traversal of a graph without defining that canonical ordering of nodes and sort of precedence, you can end up with many um, equivalent representations of the same molecular structure, just in different string forms. So that is something that's relevant for other tasks.
Right, makes sense.
Now here, right, this is sort of showing human experts writing down everything. We instead, and plenty of others, also try to learn these kinds of transformation rules from data. So chemical publishers over the past 100+ years have curated these databases of chemical transformations. And so we have a really rich history of information to use to infer what reactions are possible. And so each entry in a database that typically will have millions of such entries will tell us what reactant molecules were used, what products were observed, aspects of the conditions that were used. So if there was a catalyst, a solvent, how long the reaction was run for, the temperature, the yield, or sort of a measure of performance, as well as bibliographic information. And so, a chemist will look at this and think that there's a whole bunch of missing detail, and they'd be correct, right? All the detail that we actually need to run this reaction in the laboratory is found in the original paper or patent, but we can still take the information that is tabulated and try to use that to train models. So we're going to train sort of various types of statistical learning algorithms to learn what kinds of reactions are possible by looking at these precedents from the past 100+ years of the published literature. Now, to do that, right, to learn from these reactions requires sort of treating them a little bit more formally as a data structure for statistical learning. So this is one way of drawing a single step chemical reaction, right? It transforms this reactant into this product. It uses these two reagents, MCPBA, this drawn out molecule, and this iron chlorate catalyst. And it uses acetonitrile as a solvent. It's run cold for 1 hour. Now, this information can be captured in a number of different ways. So typically, we'll lose the quantitative aspects, just say that up front. And to write this as a string, we can do that depth-first traversal of these different graph structures and encode it in this sort of linearized and tokenized pattern. So we sort of have the red reactant characters. We have one sort of angle bracket, right, separating the reactants from the agents in the middle, then another angle bracket separating that from the product in blue. And this string representation is an acceptable way of encoding this reaction, and we can use different translation approaches to process them, right? So you can throw this in a transformer and do some things with it if you'd like. There's also lots of approaches that are trying to be more tailored to the graph structure representation of molecules. So we in particular, on this sort of fourth item, like to represent molecules as graphs. We'll elaborate more on the next slide. And there's also this notion of a condensed graph of reaction, which is sort of a graph. It is a graph data structure still, but it's been augmented so that there's different edge types where the new edge types can capture the changes that occurred during a reaction. Right. So implicit in this chemical transformation is that, the carbon atoms that you see in red are the same carbon atoms that you see in blue. And what's changed is that you've added this oxygen atom, which comes from this reagent in brown. And so there's this sort of representation that somehow brings together the reactants and products, and you might pretend that this is like a transition state of a reaction. Now, physically it's not, but it's like a transition state. It sort of captures the graph edits in one graph data structure. And so this is a convenience compact format as well. Now, like I said, we like graphs. We use a ton of graph representations in the group for many tasks. The idea is that atoms are nodes in the graph and bonds are edges in the graph. For the most part, bonds are not directional. It's an undirected graph. It can be cyclic. And I want to point out, in the spirit of the historical approaches I mentioned as well, for 150 years, people have been conceptualizing molecular structures as graphs. Even before they called them graphs, they called them diagrams, but it's the same idea of having atoms connected with bonds, obeying some physical constraints over what's allowed. And so we use quite a lot of graph neural network approaches to represent these structures. And I guess we really benefit from these representations because they'll implicitly capture conformational flexibility. And I think there's probably some folks listening that think more about sort of atomistic simulations where every atom might have a three-dimensional coordinate assigned to it. We typically don't use those representations for this level of abstraction because reactivity is a property of the identity of the molecule and the full ensemble of conformations that it can access. It's not just a property of a single three-dimensional snapshot. And so I like how the representation of a molecule as a graph implicitly captures that kind of flexibility. That's one of the reasons why we work with this representation.
Oh, to what extent is it important to capture the 3D structure? I'm thinking like protein folding tasks.
Yeah, so when properties of a molecule are properties of a specific three-dimensional conformation, like the energies and forces or the binding energy for a specific ligand protein pose, it's quite important to capture that 3D information because it's necessary to specify the problem. If you're talking about, in general, the binding affinity between a small molecule and a given protein, that is a function of the full ensemble of states that small molecule can access. And so if you know what specific conformations or poses are most relevant for binding, that information can help. But in general, that information doesn't directly help.
So in other words, because you're focusing on small molecules, it doesn't matter so much for the small molecules. And for the proteins, you can just say what's accessible, and that's a good enough approximation.
Yeah, well let's say that the connectivity implicitly defines the structure in the same way that a protein sequence implicitly defines likely, folded conformations for ordered proteins. And so there's, a lot of the properties we try to predict of small molecules are implicitly accessible enough from this graph representation. When we generate conformers of molecules, we typically do so starting from this graph. Right. And so if you want to be really pedantic about like the universal function approximation theorem, the information is there. It's just a matter of whether it's useful to express it explicitly as three-dimensional conformations or whether it's okay to keep it implicit in this sort of graph representation.
Right.
Yeah. But different problems demand different representations, I would say.
Right, that makes sense. Thank you.
Yeah. I guess on that note, graphs don't get you everything, and graphs lead to some ambiguity. And this is going to get a little bit more into the chemistry side of things. But there's this notion of chirality that is quite relevant in organic chemistry. So it's a notion of having sort of non-superimposable mirror images, like our hands, right? The graph connectivity of our hands, if you think of it like that, is identical, but you can't superimpose them exactly. They're mirror images, and they will interact with chiral environments, like left-handed scissors, in very different ways. And so it's the same thing with small molecules and proteins. So if we just represent molecules as graphs with no consideration of this aspect of their structure, we can't distinguish them. Graphs also tend to define edge features based on covalent bonds. And when we think about covalent bonds, it's really an abstraction that chemists use to think about electron locations and how electrons are distributed. And so there's notions of sort of resonant structures where molecules, we might draw them as interconverting between many different representations to capture the delocalization of electrons. And so this leads to some ambiguity in which representation is most applicable for the task at hand. There's all sorts of other complexity with regards to some chemical structures where bonding is not really between pairs of atoms. This sort of ferrocene ligand, iron, is associated with all 5 carbons of this cyclopentadiene equally. And so it's unclear how one should represent this as a graph structure. And then there's other forms of chirality where these sort of 2 molecular structures can't interconvert. Right? The way to read this is, the bold lines are coming out of the page towards us. And basically it's this macrocycle where normally you'd be able to sort of spin around that sort of phenyl with the bolded edge. But because of this methyl group, it's a hindered rotation, so it can't actually interconvert. And that sort of subtlety is not something that is well described by basically any method that we currently use for statistical learning. So there's a million edge cases that maybe shouldn't even be considered edge cases that make this still a rich problem when thinking about molecular representation. But I want us to come back now to the sort of original task that we had started defining about retrosynthetic analysis, and the idea that you can learn these patterns from data. You don't necessarily have to ask experts to encode the transformations. So as an example, if we go back to that reaction that we might see in a database, we can look at the chemical structure. We can focus in on only the parts that changed in their connectivity. We can define some local chemical environment, and we can record this transformation as a general pattern. And so we define our own subgraph rules heuristically that say, if you identify this substructure in a molecule you'd like to synthesize, here is a transformation that generates a potential reactant molecule that could be used to make it. And we can apply this sort of heuristic to millions of chemical reactions to get hundreds of thousands of rules, and we can train policy networks to learn to recommend these rules. So we have this course definition of the rules of chemistry, and we have these policy networks that learn which rules to apply and when. Right? That's the backbone to a lot of current data-driven synthesis planning programs, especially the commercial ones, I would say. But this one-step retrosynthetic analysis task, right, as the subtitle hopefully conveys, is a much more general problem. It's a very general problem of taking a product molecule as input and returning one or more reactant molecule structures. And so, of course, any architecture that is capable of taking a molecule as input and outputting one or more molecules can be applied to this task. And so I already mentioned that there's this string representation of structures. And so you can use, back when people use RNNs, LSTMs, now you just throw it in a transformer to translate between a product and reactants. You can also use graph translation approaches and hybrid sort of graph encoders and SMILES decoders to do this as well. Right? But the idea is that we have labeled data that gives us examples of pairs of reactants and products. And so we can train models to convert from products to reactants, which is exactly this single step retrosynthetic analysis of working backwards in transformation space. And so if you can do one step, you can chain multiple steps together. And so the way that we find full pathways to molecules is through the recursive application of one-step strategies. So we start with a product we'd like to synthesize. We query a one-step model to propose reactant structures. We get many suggestions typically. Then if those structures are not leaf nodes, or if they don't satisfy termination criteria like being commercially available, we further expand and further expand and further expand. And so this becomes a very large search tree, right? Grows exponentially with the increase in reaction steps. And so to rein in that complexity, people use Monte Carlo tree search, different sort of heuristic best first searches, proof number searches to try to manage this space and learn how to navigate these options. So there's a few interesting aspects of this problem worth emphasizing. One is that it's not just like a network search, because we are constructing the possibilities on the fly. So it's not just a matter of taking a molecule we want to make and doing a normal sort of graph search to connect it back to Bibles. We have to generate options on the fly, and it's not free to do that, right? So that takes some resources. These also aren't linear graphs, right? We have branching that happens, and so if you split a product into two reactants, you have to know how to make both of those reactants. And so sometimes people represent this space of possibilities with hypergraphs instead of normal graphs. And then you might think, well, if you're using these tree search algorithms like Monte Carlo tree search, a natural question is, well, can you just apply, alpha zero and techniques from reinforcement learning to learn how to do this very effectively? But there, the challenge is that we don't actually have the rules defined perfectly, right? Models that propose one-step disconnections give us an approximation of them, but we don't just have rules that we can fully exploit and learn through self-play of millions and millions of iterations to just solve this task, right? If we could clearly define the rules of chemistry and say exactly which single steps are possible and which aren't possible, then we could solve this, right? Then we could fully solve this problem of retrosynthetic analysis. But it's because we have an imperfect set of rules and an imperfect tree search that we have to sort of cope with what we have at the moment.
So
we have
question.
applied our... Yeah, go ahead.
At what point does this thing start hallucinating? Because once you get down a bad tree branch of the search, you can just invalidate the whole thing.
Yep, exactly. And so that's a problem. And actually, when we use RL for this task, what we find is that the agent typically learns to exploit the, let's say, the more optimistic rules, right? So rules that wouldn't actually work in practice, but seem very strategic because they, break some particular kind of bond. Experimentally, that will fail, but the agents, if we just let it self-play, will love to use that strategy, and it'll focus on it, and then we'll end up with a lot of pathways that all have that very critically erroneous step in them. And so there's...
Go on.
I was just saying that there's some, notion of risk mitigation also, because experimentally, if you take this recommendation of a pathway and you start putting it into practice, you're going to start from the leaf nodes, right? What you can buy. And so if you have sort of risk of failure distributed throughout this pathway, that sort of maybe, let's say that this final step is what you're most uncertain about, that's pretty bad, because that means that you could spend a ton of experimental effort getting to this final stage, making these intermediates, only then to realize that that disconnection was not feasible, or that reaction won't work. And so there's some notion of wanting to assess risk, to localize risk, to suggest experiments to de-risk these pathways, because you will end up with models that hallucinate or at least use things that will not succeed in practice.
So yeah, this is actually where I was going for with my question. To what extent can you use simulation or layers of simulation? Because these generation rules, they're just a really coarsest level of simulation. You can just you're checking the ones that are more compute time, but checking the ones that are more critical for your success.
So in general, right, the detailed evaluation of the feasibility of any one of these routes, computationally, the detailed computational analysis of individual reaction steps is something that is typically done for, one reaction will be studied in detail in a publication, right? It is a time-consuming, laborious effort. There are some automated computational pipelines for evaluation that can be used in some circumstances. I'd say that the most successful applications for those are in other domains, like combustion chemistry, rather than sort of pharmaceutical chemistry. And the reason for that is when you run reactions that don't need condensed phase solvents, right, our ability to estimate energies is much better. So even understanding how running these reactions in solution affects performance is something that is practically intractable at the moment. The other thing is if you run at high temperatures, then a certain error level and energy will lead to some difference in rate constant. But if you're at very low temperatures, some error in energy estimate of like a barrier height or an activation energy will lead to larger differences in rates. And so it's sort of more penalizing. And so I'd say that we and others are trying to work on more critical evaluation to assess feasibility of these steps, but that's very much, an open problem and is incredibly difficult to do in a general purpose way.
So then the thing I didn't get here is this, you're pointing not at computational issues like molecular dynamics is too expensive, but it sounds like it's hard to set up. It's more of a human barrier.
I'd say it's not that it's necessarily just expensive, but it's hard to set up. It's not accurate even when you do set it up. The failure modes of those calculation pipelines are not as straightforward as to just sort of, you get an output file and you know if you can trust it or not. I'd say that it's a lot of the transformations that we talk about here are just somewhat out of scope for first principles methods at the moment.
Okay.
Part of it's human setup, part of it is just accuracy. And to make things worse, here, at this level of abstraction, what we consider to be a single step, right? So if we take this particular error that I'm highlighting as an example, we write this as one step at this level of abstraction, but this, right, in reality, this would be a metal catalyzed Suzuki coupling. This would go through probably 5 or 6 intermediate states. It involved metals. It would, to actually computationally evaluate the feasibility of this from first principles requires expanding it into the individual elementary steps, evaluating each of those, and then you have this sort of massive propagation of error effects.
Okay.
But it is true that I think that more critical assessment of feasibility of these transformations is something that people are quite interested in. And again, there's this level of abstraction where people might train models to predict reaction yields. So just given the species predicts whether the reaction will succeed or not. But then as you go deeper into lower levels of abstraction, then you have the opportunity to apply first principles approaches. But your ability to do so successfully is not stellar at the moment.
Right. Okay, thank you.
Yeah, that's sort of why we're sort of forced to work at this higher level of abstraction to some extent. Now, after we get these sort of pathways, and I'm sort of skipping over a little bit of detail here, but after we get these pathways, right, one of the other tasks that I said we have to think about is filling in the details of how one actually runs this transformation. Oops, sorry. My keyboard is starting to short, so sometimes it gets stuck. Okay. So we need to figure out how do we actually run this transformation. And so here, right, if we go back to this example from the literature, it's not just that you use this reactions to make this product. That's retrosynthesis, but it's how did you do it? And so what we do is we train models to basically recover the conditions. So we can mask them, we can train it to recapitulate them, and this can be treated as either a generative problem or a supervised learning problem. This is something that we've been working on to various extents for quite some time. Actually, I'll show some results, and I've been showing this for about 5 years, but it's still quite fun. So when we train a model to help predict what reaction conditions to use to carry out the transformation most effectively, we train it just on data, and we treat each chemical species as entirely distinct. And so for this model, there's no notion of one chemical structure being similar to another chemical structure. But after we train it, right, we can get the learned embeddings for each of those molecules. And what we can find is that the model learns a pretty sensible organization, if we just project it down, of the role of these different structures. And in the loosest possible way, right, this is reminiscent of the very classic word embeddings, which, again, in the very idealized sense, capture semantic relationship. And here, at least, we can capture semantic relationships between species that operate in similar ways and species that operate in very different ways. And so the coloring and the annotations you see here are just added by humans sort of post hoc to see how has the model organized its latent space. It's not something it was aware of when training. So I always think this is fun, at least as a sanity check, to see that there are real patterns in the data that we can pick out when we train models.
Oh, you just made the periodic table of elements.
Yeah, so it's
literally how it was made.
Just natural organization of things based on how they're used.
Yeah.
It's encouraging to see. So these kinds of models and things, just to sort of maybe do a short shameless plug. Over several years, we've been trying to package these up, make them available through this software suite that we call ASCOS. So again, it's been in development in various states since 2017. And we really just try to bring together a lot of the different predictive models that we and others have built for retrosynthesis, condition prediction, product prediction, classification, atom mapping, a lot of different tasks meant to support synthesis planning in a very broad sense. And at the end of last year, we underwent a pretty major refactoring to move from a monolithic architecture to a microservice architecture, just to make it a little bit more sustainable and extensible. And so it is fully open source. The code's all up on GitLab. We have a small public deployment of this, but it's easy to also spin up your own cloud instance and run it. Well, some documentation. And if you're someone who might be interested in using or building on top of these kinds of approaches, or even contributing to ASCOS as an open source tool, that would be terrific, and would be excited for you to get in touch. Now, even though a lot of like the basic capabilities are there, right, and new predictive tools and models are being added sort of constantly, there's a couple of limitations that I want to point out in the last few minutes that we have. So one thing is that synthetic molecules are changing in their complexity. So there's this nice example from Drug Hunter last year where they showed basically this direct comparison between AZT as an antiviral for HIV. Originally reported in the late 80s, it's very simple. You could make it in 3 synthetic steps. And then more recent, right, HIV antivirals are much more structurally complex. And more important than being structurally complex, they're synthetically complex. And so to make lenacapavir takes a lot more synthetic effort. And this makes it obviously a much harder search problem, because a depth 3 search tree, that's quite tractable to do. Our branching ratios tend to be, let's say, between like 5 and 100. And so this is not a problem to explore, but once you end up having tens or 20, 30 steps, that can become very, very intractable to explore with anything close to an exhaustive thoroughness. And so you really are trusting your policy networks to guide you in the right direction. And so improving these techniques to let them tackle the complexity of modern drug targets, not just older drug targets, is something that we're very actively working on and interested in the group. The other sort of challenge is that sometimes, depending on the molecule that we're trying to make, we might end up with 0 options, or 1 option, or thousands of options, right? And so in this visualization, if we have this particular drug substance we want to make, in maybe 15, 20 seconds, we end up with hundreds and hundreds of possibilities for how we might make this particular molecule. So each one of these little branches gives us a different idea of how to produce it. And so then the question is, okay, we have all of these great ideas. What do we actually do experimentally, right? And so even though we have this really nice, successful ideation, we really have to worry more about scoring. This obviously just came up, this question of taking these ideas and critically evaluating, maybe with first principles approaches, the feasibility of a transformation. That's absolutely something that we want to use, right? So feasibility is a key aspect of how we evaluate these pathways. We might try to predict for pharmaceutical applications what impurities might be formed in the reaction. Obviously, there's some pharmaceutical impurities that are not tolerable, some that are able to be separated easily. We can think about sustainability, overall sort of yield or productivity, the cost of running this, if it can be automated, if it can scale. And so there's a lot of depth, right? A lot of domain-specific questions that one could ask about how do you take hundreds or thousands of pathway options and start to evaluate them and compare them through these sort of objective measures of pathway optimality. And so there's a lot of work to do here. Now, some of this work is possible with the current data sources we have, and some of the work is not quite possible. And so this is where we sort of always come back to the realities of statistical learning approaches that are dependent on data rather than simulation for their learning. And we can think about, for synthetic organic chemistry, having this sort of data landscape where we can think about two different axes of diversity here. So we've got the diversity of different molecules and reaction types. So types of structures and types of transformations. And on the y-axis, we have the diversity of conditions. So what base catalyst do we use for this particular reactants to products transformation? And folks who are sort of in domain might recognize that some information sources are quite rich in this type of diversity. So journal articles and patents have a lot of different structures and a lot of different reaction types, but not a lot of different conditions for each of those. Whereas our high throughput automated laboratories tends to be better equipped to generate very diverse categorical conditions, but not very diverse substrates and reaction types. And so there is some argument to be made for trying to develop really focused data sets that help us learn the effects of both of these axes at the same time. And so one of the efforts that I'm involved with is called the Open Reaction Database, and that's really an effort to try to change the landscape of data sharing for chemistry. So this is going to be more relevant for, again, folks who are closely in domain, but the ORD is really trying to support all of the machine learning efforts that are happening in this field of synthetic organic chemistry by creating data that is better suited to these goals and to promote at the same time open data sharing, reproducibility, and other sort of benefits for the chemistry community more broadly. And so, at one level, the ORD is a data structure. At another level, it's a database itself with data. And then it's also a sort of, shift in how the community should think about its own data keeping practices. And to make things a little bit trite and oversimplified, people often ask, what is the AlphaFold moment for blank? So people ask, what is the AlphaFold moment for chemistry, and what will it take? AlphaFold benefited from decades of well-curated data through extensive human effort, clearly defined benchmarks, quantitative evaluations, and all the infrastructure was present for it to benefit from in the end. And you can't have well-defined quantitative success if you can't even quantify what success means in your field. And you don't have the same curation of data. So the ORD is trying to help us along that direction, in a sense, in the field of synthetic organic chemistry. All right, so I think I'm not going to go through the discussion of analytical chemistry. Suffice to say, right, there's a lot of interesting questions about, here you can see the subtitles, spectral prediction, so understanding how molecules will look when we analyze them in complex environments and mixtures. And then the reverse problem of measuring complex solutions, like maybe if it's a water sample from a river, if it's human blood or plasma, right? And just trying to understand what are the chemical structures present. It turns out that a lot of the time we don't know, right? We obtain measurements using mass spectrometry, but we can't actually identify the molecular structures that make up our environment in our bodies. But because of time, I'll just close and skip over to some take-home messages, and really only talked about some of those work on synthetic organic chemistry, this landscape of problems that tend to operate at this higher level of abstraction using statistical inference more so than first principles simulations. This is still a challenge for the fields, even 60-something years after initial approaches. ASCOS, again, is our version of some synthesis planning tools that provides a very nice platform to build upon in an open source ecosystem. And if you're interested also in synthesis more broadly, there's a short comment article from last year in Nature Computational Sciences, just highlighting some of the questions and challenges and opportunities for the fields to address. Again, because of time, I'll just close there. Thank the group and thank generous funding support over the years. And thanks again for the chance to share some of this work with you.
Yeah, well, thank you very much. Are there questions on the call?
Yes, yeah, I had a quick question. Hi, this is Zach Wu from GDM. Great talk, Connor. I did have one question, and I might relate to what you had on reaction discovery. But specifically, a lot of your talk is based on like retrosynthesis, so like finding pathways from building blocks to complicated molecules. But are people still interested? Are you interested in developing like new edges in that like transformation path? Are people happy with the Suzuki couplings, or do we want like the Coley couplings coming up next?
I'd say people are very happy with Suzuki couplings, but still, yes. I think that the question of how do we retool some of these approaches for reaction discovery is quite interesting and quite relevant. So we have been doing this, and others have been thinking about how we can start to discover new reactions with these kinds of approaches. I think there are 3 criteria to keep in mind. So a new reaction has to be novel by a definition that a chemist would care about. It has to be feasible, which is one of the more challenging things to anticipate, but in principle has objective measures of feasibility, and it has to be useful. And so if we think about sort of the vast space of possible reactions that could exist but don't yet exist, we're really trying to use those 3 criteria to narrow down how do we focus our efforts. And so you could start with this sort of utility question to say, okay, what transformations, if possible, would make my graph more connected, right? Or shorten the pathways, etc. You could start from the feasibility question and use physics-based methods in reactive molecular dynamics to just search in an unfocused manner for what reactions seem possible. Or you could start from the novelty angle and just start to, in a very non-targeted way, generate new reactions and have your first pass be novelty. So we are thinking along those directions. I'd say that the burden for meeting those 3 criteria of novelty, feasibility, and utility, that's a high bar. That's a very high bar to meet.
It is kind of, do you know a specific example where this has happened in the past? Because I know at least for like metabolic pathways, we're pretty confident, for example, that we might know something exists. We just need to identify the enzyme in E. coli that does this thing. Right. But do you know if this like, has this been successful in the past? Is there like a case example that everyone points to?
Yeah, I'd say chemists can have very different definitions of novelty, very different definitions, right? So finding a new set of substrates that undergoes a transformation that we kind of know how to do already for very similar substrates, no one's going to think that's new. No one's going to care about that. If you have a transformation, chemists publish new methodology all the time, and we'll describe sort of new reactions. They'll often get branded as like, instead of the blank new coupling, it is the like blank type coupling, right? Where that's sort of an old version. And so I think the question of what constitutes something new and substantially different as deserving of its own name is a super divisive topic. And some people would potentially argue that the last reaction to really be discovered and hit mainstream usage was the Buchwald-Hartwig aminations, which at this point was quite some time ago, right? really fundamentally new reactions don't get discovered with that high of a frequency, but it depends on who you ask.
Cool, thanks.
Yeah, and then let me ask about, I mean, I'll poke on the simulation angle again, because at least in your talk, on the distribution of techniques in the field, I'm hearing data that comes from ultimately real studies, either high throughput or humans, kind of explored various chemicals, but experimental results. And a lot of stuff you covered had been more model-driven thing, where you take an experimental thing and you extrapolate a few other possible steps around that. But I didn't hear much about all the other level of precision between the two.
Yeah, so I'd say there's these sort of like more top-down statistical inference approaches from data. There's the bottom-up approaches from first principles through a number of different means, and they are very far apart, I would say, in terms of the scope of problems that they're trying to address. But that's why for the bottom-up sort of more physics-based approaches at the lower levels of abstraction, you do see progress and traction being made in domains where computation can get us an accurate enough answer to be useful. And so again, I'll mention maybe a colleague here, Bill Green, works a lot on pyrolysis and combustion chemistry and automatic mechanism exploration from both bottom-up and top-down approaches. And that's been very successful as an integration of the two. But for sort of general solution phase medicinal chemistry, type transformations, you don't really see prospective use of computation to anticipate transformation outcomes. You see a lot of it to explain what was observed. For post hoc explanations, we can use density functional theory to say, okay, well, this kind of makes sense. But how often is it actually used in a predictive way? It's hard to say.
So to what extent is it useful or feasible to maybe learn the physics based on partial information, which may be a different point in that abstraction space?
Yeah. So let's say, the one rung down from the abstraction of overall transformations, I'd say, is mechanistic or elementary steps. So you don't, it's not first principles, but you're thinking about, okay, individual intermediates that might be unstable, but sort of how electrons flow and redistribute. That level of abstraction is one that we're working in with a sort of analogous set of models, so that they at least think and generalize at this level of elementary reaction steps, these sort of mechanistic networks. That's proven to be successful, but not as, I guess, not as enabling as we thought it might be. Okay. My hope had been that thinking at that level would help you generalize better, help you, gain more insights. But it's been a little bit of a wash in terms of overall utility so far. We're still working on those directions.
Is it like not accurate enough, not enough breadth of coverage, something else?
I think breadth of coverage is certainly one element. Breadth of coverage is definitely an element of it. That's we're still trying to work on. But I think more ambitious questions of how do you infer like deep insights about reactivity from data, that's still something that's fairly new for the field, right? I'd say a lot of the learning the physics has come in the form of learning descriptor correlations, one or two variable sorts of trends. There hasn't been as much, again, discovering a principle that is worthy of a name. Let's say, if we want to set the bar there, that's still a moonshot.
Yeah, that makes sense. Well, yeah, thank you very much. It was extremely valuable.